Today, I am doing a review of Bayesian probability calculations. Bayes calculations are important in genetics because they refine risk assessments by integrating new information like genetic test results or a person's unaffected status into initial probability estimations. This provides the most accurate and personalized risk figures for your patients. Before diving into Bayes calculations, let's refresh some basic probability rules essential for genetic calculations. So the first is mutually exclusive outcomes. If outcomes cannot happen at the same time, add their probabilities. For example, the probability that a pregnancy is male, 1/2, or female, 1/2. You should add them together. Next is independent events. If outcomes don't affect each other, multiply their probabilities. For example, the probability that a family has 2 daughters in a row is 1/2 times 1/2 equals 1/4. Now on to Bayes specific terms. These should help structure your thinking. First, prior probability. This is the initial risk, perhaps at birth or based on a pedigree, before any new information is considered. Second, conditional probability. These are events that modify the prior risk, such as genetic test results or the unaffected status of an individual. Third, joint probability. This combines the prior and conditional probability. It's the probability of both the genetic status and the new information being true. You calculate it by multiplying the prior by the conditional. And lastly, posterior probability. This is your final probability outcome, which takes all of the above information into account. So the easiest way to organize these calculations is with a Bayes table. So here's how it generally looks. You'll typically have 2 main outcomes to compare. For example, has pathogenic variant versus does not have pathogenic variant. The prior row reflects the initial pedigree risk. The conditional row is where new information like unaffected status or test results are factored in. Remember, the probability of an unaffected individual not having a condition is usually 1, but be careful with penetrance. The joint row is simply the prior multiplied by the conditional. And the posterior row is where you find your final refined probability. A useful trick for posterior calculation is to ensure the denominators for joint 1 and joint 2 are the same. Then, pull the numerator from the corresponding joint to the posterior. And the shared denominator for the posterior is the sum of the numerators from joint 1 and joint 2. Now, let's walk through a classic example to solidify this concept. So we're going to talk about retinoblastoma. So to refresh your memory, retinoblastoma is a malignant tumor of the eye, and it may be inherited as an autosomal dominant trait. Now, penetrance is about 4 out of 5, or 80%. Now for our problem. Lisa's paternal grandmother, father, and brother had retinoblastoma, but Lisa is unaffected. What is the risk that Lisa's child develops retinoblastoma? Step 1. Draw the pedigree. Always start here. This helps visualize the inheritance pattern and assign prior risks. In Lisa's case, since her father had retinoblastoma, Lisa has a prior risk of 1/2 to have inherited the retinoblastoma pathogenic variant, and a 1/2 risk to not have it. Step 2. Set up the Bayesian calculation for Lisa's risk. We are calculating Lisa's risk of having the variant given she is unaffected. Now for our priors. Based on the pedigree, Lisa's prior risk to have the retinoblastoma pathogenic variant is 1/2, and her prior risk to not have it is also 1/2. For our conditionals, if Lisa has the variant, the probability she is unaffected is 1 minus the penetrance. Since the penetrance is 4 out of 5, the probability she is unaffected despite having the variant is 1 minus 4 out of 5, or 1/5. If Lisa does not have the variant, the probability she is unaffected is 1. Now for our joint, multiply the priors by the conditionals. So 1/2 times 1/5 equals 1/10, for Lisa has the retinoblastoma pathogenic variant. And 1/2 times 1 equals 1/2, for Lisa does not have the retinoblastoma pathogenic variant. For our posterior, to get Lisa's posterior risk of having the variant, take the joint probability of Lisa has the retinoblastoma pathogenic variant, 1/10, and divide it by the sum of the joint probabilities, 1/10 plus 1/2, to make this simple. Find a common denominator. 1/10 plus 5/10 equals 6/10. So Lisa's posterior risk of having the variant is 1/10 divided by 6/10 equals 1/6. And similarly, the posterior risk of not having the variant is 1/2 divided by 6/10 equals 5/6. Step 3. Calculate Lisa's child's risk of developing retinoblastoma. We've determined Lisa's posterior risk, and her probability of being a carrier is 1/6. So now we need to find the risk for her child. And the child's risk is calculated as Lisa's posterior risk to have the retinoblastoma variant, or 1/6, multiplied by the risk she would pass that variant to her child, 1/2 for an autosomal dominant condition, multiplied by the penetrance of the variant, 4/5. So 1/6 times 1/2 times 4/5 equals 4/60, which simplifies to 1/15. Thus, the risk that Lisa's child develops retinoblastoma is 1/15. Now, a couple of crucial reminders. First, always draw the pedigree. It's your visual map for assessing prior risks. Next, remember what the question is asking. Bayes calculation might be an intermediate step, not always the answer, as seen when calculating the child's risk in our example. All right, so you've successfully completed a full Bayesian calculation in genetics. With practice, these will become second nature. Give the video a thumbs up if you found this helpful, subscribe for more genetic counseling content, and feel free to share any other topics you'd like me to cover in the comments below. Thanks, and see you next time.